one of the things that we have as far as the national security systems is that the NSA has listed it on their website, 5 specific technical limitations to ensure quantum resistant cryptography really becomes the solution. Um, while those limitations are provided and they're fair, the valid limitations is they're only resistant to quantum attacks. They're not quantum attack proof. Um, those methods that we use to develop quantum resistant algorithms should be invested better in to the effort to generate and duplicate efforts to generate new quantum cryptography instead of quantum resistant. The resistance identified in NSA, especially on their security products for national security systems, that's problematic because it can be a little myopic. The information that was looked at, as far as the NSA is concerned, was only addressing quantum resistant. It doesn't address quantum proof. It doesn't suggest that they're going in that direction. But that was just the big five that they had on there. The infrastructure has both challenges and rewards, to satisfy a stronger national security system rather than a weaker one. But, regardless of the internal workings of those agencies, the statement that was made facing the public domain is, has to be taken into consideration because there are political and personality environments that exist within, government agencies. And really, the effort can swing or sway in a different direction because shouldering the effort can be passed on to the next, presidential administration because it could be directed in a way, or in a truthful way of the listed resources that were provided, but the content of those resources comes from, from another resource from the Journal of Modern Optics, but we see that single source from Modern Optics go back to list the NIST standard of what they want to do, and then they reference NSA, and there's this cycle, this cyclical application of knowledge to suggest, hey, it's been independently verified. We're going to go ahead and roll with it, and we'll see how how things go. But there are some gaps in there that the infrastructure that we have today needs to be not only developed but also consideration to develop the next uh, you know the next generation of cryptography using quantum computing, not just trying to break cryptographic keys. We're already showing that it's weaker, but full quantum base infrastructure, requires changing the very environment that is known both to the operator that we have and also to the adversary. So understanding that concern that's been raised, but it provides significant concern because weakening is it's a risk in relation to protecting of the assets, both current and futuristically deployed. So if we have cryptographic equipment that's deployed throughout the world, in the United States, and we develop this new cryptography, we got to go through and retire all of those old systems. They would be, in this case, outdated at most. If the cryptographic information is still on them and they become compromised, that can be a problem too. So there's a lot of moving pieces there. The decryption process where we talked about scaling out and pulling the cryptographic information via harvesting or side channel attacks. We need to make sure that the side channel attacks and the techniques that are stealing cryptographic keys, even with a radio transistor, that we make sure that those threats, that the amount that they're growing by is what we're resistant to in the future. So we already know these problems exist. It's just a matter of deploying, a known solution to bypass this. So if we're already going to go ahead and replace the infrastructure, let's go ahead and take it, to the next level and make it where it's side channel either resistant or side channel proof, which is a tall order to consider. We don't really want to neglect the quantum cryptography infrastructure. It raises those ethical considerations in the United States, particularly for privacy, and when inadequate investment is made in cryptography, personal information of the citizens becomes susceptible to any unauthorized access. When in the threats that we face today, we see the weakening of cryptography, not anymore by brute force. Brute force is, that's a nice, thing, to say, hey, we went ahead and got the 100% answer mathematically. But we see that subversion of technology and the subversion of cryptography instead of the direct, brute force approach. So, we have this concerns, about the individual's, individual autonomy, legal protection, of sensitive information, and the underlying ethical principles that need to be taken to bridge, a divide to make sure that the, single infrastructure that we have is made accessible to folks. We don't want to neglect the development of cryptography and the infrastructure, because it could carry legal consequences or implications because we don't reach the last mile, the last customer, including, those things like data theft that we deal with, national security risks that we covered with NSA, jurisdictional conflicts, intellectual property and privacy. Again, privacy and data theft is the big one. These are all concerns that need to be prioritized and invested in these areas. And our government and organizations, they need to recognize the legal imperatives and take really the proactive measure to invest in those quantum technologies to, safeguard our data, safeguard our privacy, and secure, the information of the individuals and also all of our nation, our national partners, and making sure that, the United States, when we go through and do the tempest hardening and we build the new infrastructure and, we move from a state of classical computing to quantum computing, that the United States still remains the ally of choice regarding cybersecurity. That's the big key. We've got to talk about bridging that divide. We don't want to neglect or do any of that stuff that will cause, issues regarding, things like distance. We mentioned distance before, regarding, human capital, but we're jumping into more of the technical items as far as the quantum noise and distance. The technical implementation of quantum cryptography involves a couple of components, and the big one is, photon sources, error correction, and then also quantum noise. And without getting into highly technical information, but we need to be able to make sure that using quantum cryptography and quantum mechanics, that we can send quantum key distribution and the QKD across long distances. Practical information is only as good as, as far as you can send it. So if I can send it from here to the table, that's theoretically great, but I should be able to send, and it might be a tall order now, from here to across the street or from here to Spain, and those protocols and, those things that are needed are, for the next generation to come. We're talking about, the long distance as far as, how we deploy it, what we deploy, and when we deploy, quantum cryptography, and showing that the distance problem can be solved. Do we invest in quantum repeaters? Do we use, things like the current infrastructure as far as, the fiber optics that are being laid down even today, to make sure that that problem will not be a problem in the future? Or do we need to lay more, fiber? Do we need to lay better fiber? And then also, as quantum signal transverses, an optical network, the system, if the farther the quantum packet travels, the more noise it obtains. So we have to make sure that noise is minimized, and to make sure that the packet that's received is completely intact before it drops off, or we get a packet loss across the network. So we don't know how many repeaters we'll need, we don't know how much fiber we'll need, and we need to understand how we can do all of these things all at the same time. So it starts on the laboratory bench and goes from there. Because we're talking, we're transversing in the United States, our unique geography, everything from, low swamps in in Louisiana all the way up to, the highest mountaintops in, Chicago, and then over, or not in Chicago, but in Colorado, and then all the way over to Washington, D.C. and points south that, deal with beaches and, fault lines and those type of things in California as well. So it's a big job. So we have to make sure that we can distribute those keys and understand where things are going as far as that type of technology and its deployment. For our expert panel, this is really getting into the data of what we do. A lot of this information was background and where we're at to kind of set the stage to understand, hey, this is where we're at. Here's where all the problems and the issues lie. Let's see how we can fix this. But one of the ways that we have to look at fixing it is talking to folks that are in the field as far as interest. We want to gain, folks that have at least 5 years in modern cryptography, information assurance, or those that hold public positions of trust in academia, industry, or government. We want to really understand how these cutting edge developments and challenges regarding society and cryptography, as well as bridging security and information assurance, bring light to the things that we're already talking about, and that the problems that we find out from the expert panel, are they reflected in literature, and are we seeing them in society as well? So getting those insights directly from the most qualified and experienced sources is really thoughtful, to design, and curiosity to look and say, hey, let's take a look at the mirror from a different perspective, from different outside views, and let's look and see what's going on, as opposed from my view, let's look at it objectively from 5 or 6 different points of view. But that comes with, limitations, and really limitations, stating those limitations, enhances your research, specifically research, because it strengthens what the issues are and why things are designed the way they are. Our sample size is definitely limited. This was very difficult to do because there's a stringent criteria of at least having cryptographic experience and holding positions of public trust. It's an either or situation, so it can result in, if a person was in cryptography and now they hold a position of public trust, or they have one or the other, or 2 and 3, or any blending, thereof, or they've been retired for a number of years, not being able to get that, sufficient representation of all of the diverse perspectives, within the current field, that's definitely a limitation. The identifying and contacting people, for the interviews, it introduces bias, because you have to call somebody, to say, hey, would you like to participate in this voluntarily? Some folks they just decline. They say, no, I don't want to participate in this. Thank you for your time. That can skew the sample, because you now excluded somebody that you thought was supposed to be in it, and you can't find, every single person is unique, and if your subject matter expert says, I don't want to participate, you can't force them to, but then at the same time, you lose that, subject matter expertise that would otherwise be there, so if you needed something objectively presented by that person and they don't do it, well, that's just a limitation. It's nothing that the researcher can do to overcome. It's just the process that that we go through as the human element. Also, when we get into the subjectiveness about the the interviews experience, these can be, and their opinions can be also influenced by their personal bias. So there's a risk of obtaining inconsistent or contradictory information. But what we do is, in the research, we just lay out the entire interview so the reader can see 100% of what was said, and that eliminates the bias, but you can still see some folks that, they have there's one individual that has 40 years in the defense industrial base, and you can clearly see, even though the 40 years provides a rich history and really good quality data, you can also see that some of the data elements have become stale. But those things aren't pointed out directly because we're focusing on these these hypothesis situations. But it also is reflective to show, hey, let's take a look from somebody that's got 40 years, somebody that's got 5 years, 10 years. So it could be inconsistent. You might see inconsistencies with somebody that says, hey, this is how it used to be, and it may either be that way or not be that way today, depending on the person that's reading it, and including the writer. Somebody saying that, this dog used to be black and now he's gray because he's aged, that's still subject to interpretation if the gentleman that saw the dog 8 years ago is, saw him when he was black. So he's going based off of his experience. So, we've restricted the sample size pretty good as far as this, the broader population of cryptographic professionals. Myself, I don't live in Silicon Valley, so being able to interview those peoples and those, in modern cryptographic issues, or not being in Washington, D.C., that leads to, an underrepresentation, as far as limitations. And then the last one is also, of course, the time. If we only have a certain amount of time for the interview, to take place on the phone, so there's, certain topics that would not allow the participant to elaborate on a subject matter expert further, subject matter further. So if somebody has something really to say about how the defense industrial base connects well with the rest of industry, and they want to elaborate on it, but they can't because of the sake of time, then we've lost some data there. But excuse me. There are other factors that influence. We have the control over variables. One of the things is that the study addresses and requires us, here at APU, to make sure that the enforcement of ethical considerations is occurring, regarding, consent and conflicts of interest. And, given that the fact that the subjects also hold positions of public trust, they may not be able to tell us exactly what sensitive information that they know, but they can't say, either because of non-disclosure, because of national security, or because of academic policy, or all three of those components combined together. Being in a position of public trust, they may have to get a clearance to say, hey, I can do this interview. There may be other things that's just, we can't control those variables, in this. We have, the interviews, subject matter expert interviews, especially in person, they demand, a good amount of time to identify and contact and interview these participants. And then, these can be mitigated, the triangulation method, or the interview preparation, thorough preparation, and then to provide transparent discussion about, bias and limitations if they come up. As far as the information that that we have, that's all the information that we have as far as the subject matter experts. But we have our panel, our 5 subject matter expert panel, and they range from working with the youth of tomorrow, in elementary school, all the way up to training the experts of today, in the automotive industry, over to, the government of Cameroon, and then we circle back to an individual, that's worked 40 years in the defense industrial base. And really what we see is this, this current working state of, of examining, the working architecture and implementation of quantum cryptography needs to be, it's still in its infancy. And, because it's complex, it's limited because of the operation and sustainment. Oftentimes what we see across industries and across government, and when we were talking about the low risk, is that we have a really high startup cost and we implement the plan, as far as what we're going to do, but we need to make it cheaper, and those things are important, as far as supply chain and those type of things. But What about the operation and sustainment? Particularly, one of the individuals that was in defense industrial base that trains individuals in the automotive industry was really harnessing in on, it needs to be useful. And the same thing with the elementary school, professional, was that this information not only needs to be useful, but it also needs to make sure that it has operations and sustainment, which ultimately means we start talking about budgets. We didn't talk too much. I mean, as far as the literature didn't specifically mention what the long-term benefits are as far as developing commercially available cheap quantum repeaters, to extend those fiber optics, to the last mile customers. We see that really in, in telephone and in DSL type internet or satellite internet, your Starlinks and things like that. But in industry, there was two things that we did in literature and in industry that we didn't see, is that there was no long-term plans for developing quantum cryptography in quantum computers networks commercially ready, and that the quantum repeaters that are needed to install to keep the distance problem, there's no plan right now to reduce the cost of those as far as getting it to the last mile customers. It's not even a thought. It was one of those things that we pinpointed in the literature to say, hey, there's a distinguishment here between, the copper wiring that we use for, basic telephone, to the next generation of quantum cryptography, quantum computing, and fiber optic networks that wasn't talked about. It wasn't addressed, and it's not available in any of the research that I was, looking at as far as my, references. Customers, they're going to become dependent on this. One of the things that the new generation that's being born today will be those that will age tomorrow. So answering how this type of technology is going to be deployed and getting a firm grasp on it is what the United States needs. But given our current socio-political environment, is definitely one to note. We have some really difficult questions that we have to answer as far as, what we need to do to achieve that. Is the quantum cryptography, quantum computing problem, is that going to be made accessible to people that are, are older? Is that quantum cryptography going to be accessible to those that have disabilities? Is quantum cryptography going to allow for secure communications of those that may not otherwise be able to make a decision one way or the other as far as legality, like minors? Allocating the amount of time to train individuals on this new technology. Those are things that are definitely asked and considered here, but considering the gap that we're not even addressing the last mile customers is really a problem that needs to be addressed first ahead of all of the other ones. We need to have the infrastructure and the lights on before we really start to address those training needs and stuff, because we have to see what we have. Secure communication through those exchange, through the mediums of what we need exchange using those principles of quantum mechanics protocols. So we want to make sure that we are promoting, the inclusivity of the, participation, not only in research participation, but also fairly identifying where all of the holes are in order to understand where we need to go. When we leave out the last mile customers, we're leaving out, folks that don't understand, they don't need to understand why quantum cryptography matters. They just need to go in and maybe check their bank account. Somebody that's elderly may be able to need to see, something with their Social Security deposit. Communicate to the government what those needs are. Those constituents relay their information up into the government, and it hits a legislative bench. There are other issues about the usability, for our youth, and one of our subject matter experts was, public education, is that it has to be useful. People won't use it if it's not useful. One of the benefits is that cryptography today works in the background. We take it for granted, and just like anything else, just like the air we breathe, cryptography in the background it's really a good thing, but we need to make sure that it's still just as easy to use. So if there's a problem, we definitely need to address it. In industry, we also need to make sure that we're partnering with NATO partner nations. One of the things in the literature that wasn't pointed out, but was pointed out by our subject matter expertise, was we need to invest in making sure that we're crossing international borders to understand what they're doing and what we're doing, and making sure that we align, common research goals and common research things, so we're not having a duplicative effort. It's a heavy draw, because this gentleman is up, at the tip of Niagara, and they have influence from the government of Canada, where somebody that maybe at the central Nevada, they don't have any influence or any of that type of stuff because of Toronto in the north. It doesn't exist. But that inclusivity, from various age groups, backgrounds, abilities, and seeking that input and feedback from a very, very diverse user base, and getting that usability and security and benefits for those, future and current cryptographic algorithms for today and also for tomorrow, for a wide range of individuals. We want to make sure that we also tailor and understand, especially with a baby boomer generation, that the design of what we do for quantum cryptography takes into consideration the ethical consequences and benefits of including things like the elderly. We always include the youth, but also including the elderly population. This will be including ourselves, in the next 40 to 50 years. How these systems should be deployed with the specific needs and preferences of older users in mind. We need to look at, including things, on screen for larger fonts, intuitive interfaces, easy instructions, anything that's user-friendly, the design elements that are used to indicate that, to say, hey, to this person, a simplified view to say, hey, your information is 100% secure. Here it is, and those things, there's future pressing needs, as far as developing, the cryptographic, the interfaces that are ADA compliant, and 508 compliant. They gotta be, the utmost consideration for the betterment of society includes individuals with disabilities. Things that we need should also include things like screen readers and keyboards and navigations and assistive technologies that are compatible with the new cryptographic standard. We don't know where this will lead as far as overcoming the other issues that we have as far as the infrastructure, but making it usable to all people, this type of approach will guarantee that individuals, regardless of their physical or sensory abilities, can actively engage in, secure communications, with those the platforms that will eventually be coming in the future. It's a really big deal. It's exciting, but we also have to make sure that we're not moving too fast, that we're not excluding people either. So we're going to go back and restate our hypothesis that we have. We see that the 256, the algorithm is becoming weaker. They're turning it into quantum computers are turning this problem of where AES 256 will fall in a matter of hours. Hopefully, it'll be the driving force to say, hey, they can do it in a couple of minutes and really put the squeeze on. But right now, just like Diffie and Hellman had said, it's really expensive right now, but perhaps in the future, I'm iterating that AES 256 is not going to be as strong as we think that it is in the next generation. With a quantum computing infrastructure, with it being feasibly deployed in the public domain, can definitely be done in areas that have, the current fiber optic infrastructure, maybe some quantum repeaters. It can be feasibly deployed, but we need to test it. We're testing the short distances, but we're not testing the medium and the long distances. And medium and long distances those are relative terms. Short distances are like your couple of feet, and then your long distances are like your kilometers, like a couple thousand kilometers. So, research talks about 1 kilometer being long, but I'm talking long distances. So it's feasible. We just got to get there. So part of it is making sure that those costs come down too. So we've shown a quantum key distribution provides greater security than other key distribution methods because it's purely random. We don't have to depend on a pre-shared key. We just distribute it and we're good to go. So we see also that the 4 goals of cryptography, we talked about all of the, the CIA triad and the non-repudiation. Those are the things that are inherently, in order to develop and use cryptography, those things are inherently built in to quantum-based algorithms. That's the whole purpose of developing those type of algorithms and across that infrastructure, was to make sure that all of those things are definitely true. Being practically deployed on the quantum key distribution on classical computing can still be proven to be difficult. With the practicality, I mean, we're talking a classical computer. They're not built for, they're not built for quantum mechanical systems. So this one, we'll have to see if there's a type of bridge. We don't know the answer to this. Is it practical? That would be great if we had a solution, but we don't know. At the current state of things, can it be done? Because we can't go more than maybe a kilometer of distance, to distribute a key. A key can be distributed, but can it be done on a classical system? That's the trick. We talked about the collection and harvesting with the transistor radio. In the Tempest hardening areas, it's Van Eck radiation, so we're talking about harvesting that information. If it's occurring in literature, that literature is available to the adversary, and the adversary is reading that literature, and they're developing the same thing to harvest the information. So we talked about the error correction and the noise issues that are being addressed in quantum computing. Well, with that stuff being minimized, for practical deployment. And making sure that those handful of things are definitely addressed. So I will go ahead and turn this back over to you guys. There's a list of my resources, and if you have any questions, please let me know. Thank you so much.